Alright, hey guys, welcome to our first video. We're doing major air pollutants and their sources. This is module 46. Hopefully you have some time to sit down and watch this video and do this lecture with us. You're not required to. I'll post this PowerPoint, but I think it could be beneficial. Some of you like hearing it instead of just reading it. So this is for you. I'm going to try to go through this as quickly as possible, although this will probably be a pretty long video because air pollution is sort of a big concept in this class. So feel free to pause it if you need to and walk away, or take notes as you need to. Go to the headings that make the most sense for you if you don't understand a specific part. So feel free to sort of move through it as you need to. It's going to be set up pretty similarly to how we do this in class, and hopefully it all makes sense. But if it doesn't, you can always reach out to me in any way, and I can clear things up for you. So let's get started. So by the time we get through this PowerPoint, you should be able to identify and describe the major air pollutants and describe the sources of air pollution. So we like to look at air pollution as a global system. So what does that mean exactly? First, what is air pollution, I guess, is what's important. So air pollution is any sort of introduction of chemicals, particulate matter, or microorganisms that's in a concentration that's high enough to harm living things or alter buildings or building materials or ecosystems. So this is probably something that you're familiar with. It's also important to note that most air pollution that we'll be referring to is generally within the first 10 miles of the Earth's atmosphere. So from the surface of our planet 10 miles up, that's about our troposphere, or that's within our troposphere. That's where most air pollution is occurring, and that's the type of air pollution we'll mostly be talking about. Now, looking at air pollution as a system, like most things in this class, we can look at it as a system. It has a series of inputs and outputs and a sense of storage. And we'll look on this next slide what those inputs and outputs are. You can also look at pollution as being both local and global. So I gave you guys the article on Chattanooga, Tennessee. And hopefully you read that. That was sort of the preview to this lesson. But that was an example of local pollution. Chattanooga, Tennessee was essentially sitting in a valley, and they had a ton of industrial buildings, and they were burning lots of coals and fossil fuels. And it basically all got trapped in this valley, and it couldn't move, and there was no wind to carry it away. So that's considered local pollution. Everything that they were doing, they were sort of doing to themselves. Whereas if we look at the type of pollution that we see in the west coast of the United States, that's more of an example of global pollution. Most of our pollution actually comes from China. It's air pollution that has made its way over via wind or something else that's carried it to our air. So different types of pollution that we'll be looking at. And hopefully that gives you a frame of reference for that Chattanooga article. Okay, so I mentioned that we have these inputs and these outputs for air pollution, making it this system. So our inputs are anything that's actually going to be contributing to air pollution. So things like cars or planes or vegetation, and we'll look at what that means. Those will be the inputs, what's actually contributing to it becoming air pollution. Then air pollution, as those things sit in our air, that's the system, that's the storage. And then the outputs are how we actually remove that air pollution. So whether that's through vegetation, soil, clouds, particles, gases, things like that. And we'll look at again how some of those are removed and what that means. But just to give you some perspective on how we can look at this as a system, and then a little bit of perspective again on why it's considered a global system, because we don't necessarily see the pollution that happens in one place staying in one place. It ends up kind of all over the world. Okay, so classifying pollutants. So right now, the U.S. Clean Air Act was the U.S. Clean Air Act of 1970, but it's actually been amended many, many times. Most recently in 2012. But the Clean Air Act basically says, okay, here are our top 6 most harmful pollutants to humans. They're listed here for you: sulfur dioxide, nitrogen oxides, carbon monoxide, particulate matter, tropospheric ozone, and lead. Those are our most harmful pollutants, and it basically says that these are what they call criteria air pollutants, and that each of these has an allowable concentration that can be in the air, meaning if you are somebody who's emitting some of these, there is a specific amount that you are allowed to emit. right? And so that's basically what they said. And you'll notice that on that list, carbon dioxide isn't actually on the list. And that's probably the one we focus on the most in this class. We talk about carbon dioxide emissions or CO2 emissions all the time. That was finally added into the Clean Air Act as something that we need to be aware of in 2007. So it really hasn't been on there that long. And then in 2012, there was another amendment for VOCs and mercury, and we'll look at what those are if you're not aware of what VOCs and mercury are as well. Okay, so what are these major air pollutants? We'll get into it a little bit. So the first one is sulfur dioxide. Sulfur dioxide, or SO2, is something that primarily comes from the combustion of fossil fuels, mainly things like coal and oil. So sulfur is really what is emitted, but it combines with oxygen in the air to give us something like SO2. Sulfur dioxide is somewhat of a respiratory irritant, meaning breathing in a lot of sulfur dioxide will give you like a tightness of your chest, hard to breathe, things like that. The other thing that it's harmful for is the stomata of plants. So the stomata of plants facilitate gas exchange between oxygen and carbon dioxide. So the intake of carbon dioxide and the exporting of oxygen. That SO2 or sulfur dioxide can harm the gas exchange that happens in plants. And we know that gas exchange is not only important for plants, but also us, because that's where most of our oxygen comes from. The other place that we see sulfur dioxide is, or the other issue we see with sulfur dioxide is it's how we get that acid rain, right? So sulfuric acid, which can come as a result of interacting with other things in our atmosphere from sulfur dioxide. We get that acid rain, which we know can be harmful to things like aquatic life or our plants. Those are sort of the anthropogenic causes of it. Things like burning coal and oil, so mostly cars. Cars are the biggest emitters of sulfur dioxide, or transportation that uses fossil fuels. But there's also the natural releasing of sulfur dioxide, and the biggest quantity of this is volcanic eruptions, and in smaller quantities, forest fires. So with volcanic eruptions, if you've ever been in an area where a volcano is erupting, maybe not explosively erupting, but slowly erupting, you'll actually smell the sulfur in the air. It's this very, very, very strong sulfur smell. It's like a rotten egg type smell. You've probably smelt something similar when geysers erupt, if you've ever been to Yellowstone and seen Old Faithful, right? The interesting thing about this is if you're in an area where there's a volcanic eruption and you're breathing that air in all the time, not only will you have that respiratory irritation or perhaps the asthma or something like that, but you'll also actually notice that your urine will gain a really, really strong sulfur smell. So it's kind of it's a little alarming at first, but it is possible. I kind of already explained this already, but we do see the formation when sulfur dioxide combines with water in the air, we get that sulfuric acid. We know sulfuric acid is a major component of acid rain. Acid rain can change a couple things. It can change the pH of the soil, which will inhibit plant growth. We know that if it manipulates the stomata, it can inhibit photosynthesis by disrupting that gas exchange process. Additionally, if the stomata is left open, so the stomata is a mechanism that will open and close to facilitate that gas exchange, sulfur dioxide can prohibit it from being able to close properly, which makes it left open, and then perhaps large amounts of water could potentially go inside of that, or leave it, and as a result, the plant could suffer. Okay, so that's it for sulfur. Now we're on nitrogen oxides. Nitrogen oxides, or NOxes, is actually what you'll hear them call it. NOxes they can be two different things, which is why they call them NOxes. X is generic, right? It can be NO or NO2. So you'll hear people refer to them as NOxes. So nitrogen oxide, or just NO, has just the one oxygen atom. This is a colorless, odorless gas, whereas nitrogen dioxide, so two oxygen atoms, are going to be this very pungent red-brown gas, very clear, very distinct looking. And each of these will easily transform in the atmosphere into something else, and we'll get to that. So what does this look like? So most of our atmosphere, approximately 78% of our atmosphere, is N2 gas. It's nitrogen. And combustion within the atmosphere is actually what converts this N2 into nitrogen oxides. So there can be anthropogenic or natural nitrogen oxides. So most, again, anthropogenic causes are from cars, so things that are burning, or vehicles or transportation that's burning fossil fuels. The natural causes we've kind of already discussed in the previous one, but forest fires are a big emitter of nitrogen oxides, and lightning actually as well. Similar types of effects, you're going to lead to a respiratory irritation, potential ozone formation of photochemical smog. We'll get into that just in a bit, on what ozone formation is and photochemical smog, and kind of why that's a bad thing. And again, precursor to ozone leads to the formation of photochemical smog for natural emissions of nitrogen oxides. We also see this contributing to acid rain as well, because it can convert to nitric acid. So both sulfuric and nitric acid can contribute to acid rain, and we know the negative effects of that. And potentially contributing to over-fertilizing terrestrial and aquatic systems, because we know that nitrogen and phosphorus are two things that are really important for plant growth and for living things. So excess amounts of nitrogen in the soil can lead to over-fertilization, and we sort of know the effects of that already as well. Okay, carbon monoxide. Carbon monoxide is something that happens as a result of incomplete combustion. So incomplete combustion means you haven't quite burned it all the way through, essentially. So usually this happens when your supply of oxygen is really poor. So this is actually really common when you're starting your car or things like that. The other place you may see this is, it's not even just starting your car, it's just keeping your car running. If there's a fair supply of oxygen available to your car when you're trying to keep the engine running, you are risking carbon monoxide being emitted. Most of the time your car is emitting carbon monoxide. Another place you may see this happening are places like your stove, things like that. Carbon monoxide is, like they said, it's a silent killer. You can't see it, you can't smell it, you don't know anything is happening. The most houses now are equipped with a smoke detector and a carbon monoxide detector. So you would never know, but if your carbon monoxide alarm is going off, then that would be something to take seriously. Not because your house would be on fire, but because it'll make you sick, and essentially if you breathe in too much carbon monoxide and not enough oxygen, you will suffocate yourself. Basically, what's happening with this combustion reaction is that you're getting a hydrocarbon plus an oxygen, and instead of resulting in carbon dioxide, you're getting carbon monoxide plus water. So it's essentially, you're no longer getting that CO2 emission, you're getting the CO emission. Again, vehicle exhaust is the most significant component, or most significant contributor to carbon monoxide. Now, carbon dioxide, the CO2s, this is one we've focused on a lot. Carbon dioxides are formed with the complete combustion of most fossil fuels and most matter. So really, anytime you're burning something, you're probably emitting CO2. CO2 is something that is sequestered by most plants, right? We talked about when the Amazon rainforest was burning, it was going to be not only a loss of an ecosystem and biodiversity, but a loss of a massive storage of carbon. A good portion of the carbon on our planet is stored in the Amazon rainforest. So plants use it, they absorb it, they store it. This is called carbon sequestering. we are seeing a steady increase in the amount of carbon dioxides that are sitting in the air. We've sort of touched on this all year, right? This is what everyone says is contributing the largest contributor to global climate change, right? Is this increase in CO2. And most of our CO2 is coming from the combustion of fossil fuels. This is a big idea in this class. So it's actually interesting, and your discussion topic this week is sort of looking at all of a sudden, because of this corona outbreak, we've actually seen this massive decrease in people who are using transportation because they're not leaving their house, right? So all of a sudden we're seeing a massive decrease in the amount of daily CO2 emissions. So it's actually having these very unintended consequences of like less fossil fuel emissions, right? Less CO2 emissions. And so it's kind of been an interesting thing to look at, and that's actually what your discussion post will be on this week. Okay, so particulate matter, or PM. Particulate matter can be solid or liquid, and it's something that is suspended in the air. And sometimes you can see particulate matter, sometimes it's much smaller. It ranges in size. But basically, what I would attribute this most to, or what I think of when I think of particulate matter, is when I'm driving my car down a dirt road and I'm kicking up all this dust behind the car that I can actually see. That's particulate matter. Now, sometimes particulate matter is of concern and sometimes it's not. It really has to do with the size of the particulate matter. And what they call particulate matter 10 is a size of particulate matter that can no longer be filtered by your nose. So most particulate matter, if it's of a certain size, if it's large enough, your nose, the hairs in your nose and the mucus in your nose will prohibit it from ever getting much further than that. It won't ever enter into your lungs. It'll irritate your nose and sort of that'll be it. But particulate matter 10 is the one that's of largest concern because it can't be filtered, right? And if you're taking in that size particulate matter, then that is something that ends up in your lungs. And that is something that can be of a health concern to you. The other concern with particulate matter is that if there's enough of it in the air, it can both scatter and absorb light. So if there's a lot of particulate matter sitting in the air, one, it's going to decrease the amount of solar insolation that's actually able to reach the Earth's surface, right? So you'll get this sort of like cloud, essentially, preventing sunlight from entering, right? And it can also scatter light, meaning maybe it's going in weird directions, right? Not a consistent flow of light. This will essentially decrease productivity of an ecosystem, right? If there isn't a consistent, or if there isn't consistent sunlight, or if there is no sunlight coming in, then of course photosynthesis can occur. So productivity is going to decrease because there's not enough energy enough energy entering into that ecosystem. So that's sort of a problem there. So particulate matter can cause something called haze, and that would be basically if you're looking out into the distance and it looks like there's like just a filter over what you're looking at. That would be haze, and that can reduce your visibility of seeing a further distance depending on how bad it is. So where does particulate matter come from? It can come from a lot of things. So I sort of gave you the example of your car kicking up dust, but combustion of wood, animal manure, coal, gasoline, all of those are going to contribute to particulate matter. Ones that we talked about in our energy unit were wood and animal manure, especially in lesser economically developed countries where they're using those as their primary sources of energy, wood and animal manure, and perhaps they're burning those inside their homes. Particulate matter becomes a really big problem because you're inhaling it in a very small area and it's not being distributed. And then, of course, there are natural causes of particulate matter, so things like volcanoes, forest fires, and dust storms. I think when we talked about the Dust Bowl happening, we talked about how it was super hard for people to breathe, right? The other example I could give is for all of you who aren't going to Coachella this year, you're saving yourself from the big dust and sandstorms that happen out there. You've probably seen people wearing the bandanas that cover their nose and mouth. They're trying to avoid inhaling all of that dust that when the wind kicks up. So lucky you guys, I guess. Okay, so photochemical oxidants. This is photochemical oxidants. When you see the word photo, you should assume that there's light involved. So what this is sunlight interacting with other compounds such as nitrogen oxides and sulfur dioxides and creating a new class of air pollutants. So anything that's a photochemical oxidant means it's something that has interacted with light and it's caused something new to be formed, right? So there are many photochemical oxidants. There's ozone smog, photochemical smog, and sulfurous smog. Now, sulfurous smog is actually one you're going to read about. You're going to read about the Great London Fog that killed like 12,000 people or something crazy like that in like 3 days. It was this insane, they had this insane sulfurous smog that came out. And basically, it was this smog that had such high concentrations of sulfur dioxide that was reacting with the oxygen in the air that it became sulfuric acid, that all of these people ended up inhaling tons of sulfuric acid and just dying. It was really horrible. So you'll read about that and kind of what causes it, but mostly the emission of sulfur dioxide into the air, which comes from things like burning fossil fuels like coals and oil. And at the time of this Great London horror story, it was an incredibly cold time and people were using coal burning stoves in their homes, so the amount of sulfur dioxide that was being emitted was much, much larger than it normally would be, and it kind of was this perfect storm. So you'll read more about what the climatic conditions were like during that time as well. Now, photochemical smog, this is what they call the Los Angeles smog or brown smog. It's the kind of smog we see when you stand in the back of the science building and you look over to see Los Angeles on the skyline and you kind of see that brown haze. That is photochemical smog. And this is smog that's dominated by things like ozone. And really, we see most of this. We're going to learn more about this type of smog, but mostly we see this from emissions, right? Emissions from cars and things like that. And smog, just as a generic term, is a mixture of oxidants and particulate matter. So, and then ozone is a secondary pollutant made up of 3 oxygen atoms bound together. Now, ozone is something we're actually going to talk about here soon. So, ozone we generally think of as something that is a good thing. Ozone is what protects us from too much UV light exposure, right? It blocks some of our UV light so we're not constantly getting the sun beating down on us and risking sort of biological harm. But there's stratospheric ozone and there's tropospheric ozone, and one of those is actually not a great thing. And stratospheric ozone is the type of ozone that we like. It's what prevents too much solar insolation, and tropospheric ozone is the one that isn't necessarily so great. And I think that's actually coming up in our next unit, so we'll get there. We'll come back to this. Okay, and lead and other metals. So lead and mercury in this unit are the two that that the AP wants you to focus on as types of air pollution. We've already talked a lot about mercury, but lead. Lead is something that used to be added to gasoline. It's also naturally found in oil, coal, or not naturally found. It's something that was added to both oil and coal and paint. We don't add lead to any of these things anymore. That's why when you go to the gas station, you have unleaded gasoline. Lead hasn't been added for a long time. There's a couple reasons why, actually. The first was that the lead emissions were ridiculously high. We had large amounts of lead in the atmosphere, and it's a primary pollutant that is terrible for you to be inhaling. And they needed to quickly get lead levels down, so that Clean Air Act put the kibosh on putting lead in gasoline. The other reason why they kind of took it out was they were trying to decrease other types of emissions that came from cars, so things like sulfurs and nitrogens. So they installed these things in most cars called catalytic converters, and catalytic converters are basically a way to decrease the amount of emissions your car has, and they found that the lead was corroding the material that was making up the catalytic converters, and so as a result there was really no lead put into fuel. So you actually don't have that anymore. There's no lead in paint anymore. There may be still old paint that exists in the world that has it, but for the most part, most paint doesn't have any lead in it either. Lead is something that occurs naturally. It's in rocks, it's in soils, and any heavy metal, having too much lead will lead to some sort of nervous system damage, right? And we've talked about this when we talked about how drinking water that has heavy amounts of lead in it can impact you. We talked about this when we talked about the Flint, Michigan water crisis. Okay, so VOCs, VOXs, or volatile organic compounds. These are organic compounds that evaporate at typical atmospheric temperatures. So most of these are hydrocarbons, and hydrocarbons are just compounds that contain both carbon and hydrogen bonds. So things like gasoline, lighter fluid, dry cleaning fluids, oil-based paints and perfumes, really it's things that have a really, really strong scent to them. So VOCs I always associate with something that has like a very strong smell to it. Now, the VOCs, the volatile organic compounds, are formed by the evaporation of these things, right? So gasoline, if you've ever been to the gas station and a little bit of gasoline has dripped out, or even just standing at the gas station, it has a very, very, very strong smell. Some people really like the smell of gasoline, but the evaporation of it, if you've ever watched it drip onto the floor right by where you're filling up your gas can, or onto the ground near where you're filling up your gas tank or a gas can, you'll notice it evaporates very, very quickly. That's what's causing those volatile organic compounds. These are all a precursor to things like ozone, but they're actually not on that criteria air pollutant list. Those were the ones that were added in 2012, but they aren't considered a criteria air pollutant. So we've got things called primary and secondary pollutants. So primary pollutants are something that it's the primary source. So it's coming directly out of a smokestack, an exhaust pipe, or other natural emission source like a volcano or a forest fire. Those are primary pollutants. The examples of primary pollutants are carbon monoxide, carbon dioxide, sulfur dioxide, those NOxes, most particulate matter. That's a primary pollutant. The emission of exactly that is considered an air pollutant. Many VOCs are also considered primary air pollutants as well, so things like gasoline in your car. Those are primary pollutants. The second they leave that smokestack, the second they leave your car, they're already considered a problem for the air or a pollution. Whereas secondary pollutants mean they've undergone some type of transformation, meaning those primary pollutants have actually undergone some sort of transformation. And usually that transformation happens in the presence of sunlight, water, oxygen, or other compounds. And sunlight basically is what's giving it the energy to go through this transformation. This is why you see most secondary pollutants coming about during the daytime, not at nighttime because there's no sun. So most are happening during the day. So things that are considered secondary pollutants are ozone, sulfates, and nitrates. And we already kind of talked about all those. So here's an example of our primary pollutants that we just talked about, those SO2, NO, NO2, CO2, CO, hydrocarbons, VOCs, things like that. And then some primary or some secondary pollutants that come as a result of those primary pollutants interacting with sunlight. Okay, so quick check-in, and this is where I would pause and maybe just get my thoughts together, write them down on a piece of paper, see how much you kind of gathered from that first half of the PowerPoint. What is air pollution considered, or why is air pollution considered a global system? What are the major air pollutants, and what is the difference between a primary and secondary pollutant? So pause, because on the next slide I have the answers for you. Okay, so why is air pollution considered a global system? It crosses many system boundaries. So we kind of already talked about this. One country can create air pollution that affects the air quality in other countries. So I told you most of the air pollution that's sitting on the west coast of the United States is coming from not the west coast of the United States, but somewhere like China. So that's why it's considered a global system. And what are the major air pollutants? So sulfur dioxide, nitrogen oxide, carbon oxides, particulate matter, lead, VOCs, mercury, and ground level ozone, which we'll get more to on ozone. I know we haven't talked about it a ton, but it's coming. And then what is the primary difference between a primary and a secondary pollutant? So a primary pollutant comes directly out of a smokestack, exhaust pipe, natural emission source, whereas a secondary pollution is a primary pollutant that has undergone some sort of transformation in the presence of sunlight, water, oxygen, and other compounds to form a new chemical pollutant. So they've undergone some sort of chemical change that forms a new chemical pollutant. Okay. we're getting close here, guys. So air pollution comes from both natural and human sources. So those natural emissions I've sort of mentioned here: volcanoes, lightning, forest fires. Plants, both living and dead, release compounds that can be classified as pollutants. And then anthropogenic sources, cars or vehicles or methods of transportation that are burning fossil fuels, power plants, any type of industrial processes, waste disposal where they're burning waste, like in an incinerator. We see pollution coming from kind of everywhere. Our anthropogenic emissions at this point are monitored and regulated, meaning essentially you're not free to just emit as many pollutants as you want. There's a cap that you can reach. There are measures put into place to make sure that you're not emitting constantly, right? Some anthropogenic sources are those vehicles, power plants, industrial processes, right? Things that we've already talked about. And the Clean Air Act basically says that it establishes these hard guidelines, like you cannot go over this based on it being bad for humans, right? There's something called the National Ambient Air Quality Standards, or NAAQS. The EPA periodically specifies concentrations and limits for air pollution. So the National Ambient Air Quality Standards are basically looking at, they basically constantly change what can be considered the normal level for emissions and what can't be. This is a bit blurry, I apologize. This is just looking at, the first one is for carbon monoxide, nitrogen oxide, sulfur dioxide, and particulate matter, and it's how much each thing where most of the emissions are coming from. So for the first one, for carbon monoxide, as we said, for the most part, it's cars doing incomplete combustion in their engine from a lack of oxygen. So mostly it's cars. Fires have carbon monoxide, which is why your smoke detectors oftentimes also have a carbon monoxide alarm. Things like that. We've got nitrogen oxides. Again, cars are one of the biggest ones that are contributing to nitrogen oxides. And for particulate matter, road dust, that was one of the ones I mentioned to you. Fires are on there. And then sulfur dioxide, mostly the combustion of other fossil fuels, right? Okay, so this is looking at what has changed in our air quality from 1990 to 2010. So one of the ones that I think is the most drastic is lead here, right? So it's quickly switching over from not putting lead into our fuels anymore. You can see how it has decreased significantly in the air. Okay, now here, which is not considered a criteria air pollutant. And hopefully on here, C, carbon dioxide, is not considered a criteria air pollutant, although it is now considered a criteria air pollutant. 2, a secondary pollutant forms in the stratosphere, is transformed by sunlight or water. That is true. Cannot be directly tracked, does not directly harm humans, and forms primarily from incomplete combustion. B is the correct answer there. And then, which is a source of sulfur dioxide found in nature? D would be the primary example there. Volcanoes. And carbon monoxide increases lung cancer rates, leads to the formation of photochemical smog, is problematic in rural areas, does not directly cause death, or is produced by incomplete combustion. So E is produced by incomplete combustions is the correct answer there. Okay. So this was sort of your last, that was your last slide, so for Module 46. Now you have a couple other assignments to complete. Those are all listed on Canvas. Hopefully this was just a very general overview of what you needed to know for this unit. Please let me know if you have more questions, and we'll get through those then. Okay, thanks guys, have a great day.